Now we will look at some specific discrete distributions. We've already talked about what a discrete random variable is. We have talked about the probability distribution of a discrete random variable. Those were the general cases we talked about, right? Which means that we could have we suggested using a tabular format for the probability distribution of a discrete random variable, or we could also have used a formula. We called it a probability mass function. Those were all for the general cases, right? We talked about expectation, variance, and so on. Now we want to talk about some specific discrete distributions. We will start with the uniform distribution, okay? So we are looking at some discrete distributions. We will start with the discrete uniform distribution. We will also have a continuous version for this distribution. Let's now talk about the discrete version. So this discrete uniform distribution is used to model a situation with a finite number, right? A finite number n of equally likely outcomes. Okay, let me say that again, yeah? Okay, this discrete uniform distribution is used to model a situation with a finite number, let's call it n, of equally likely outcomes. So here we are calling it x1, x2, x3, right up to xn, because we are saying there are n equally likely outcomes, right? And we are saying that this distribution is defined like this, okay? I repeat, we are saying that the distribution, the discrete uniform distribution, is defined like this. The probability that big X, of course, represents the random variable, equals to xi equals to what? 1 over n. For I equals to what? 1, 2, 3, 4, right up to n, okay? So this is your probability mass function for a discrete uniform distribution. Probability x equals to xi equals to 1 over n, okay? I going from 1 to n. So let me just remind you of an example, a simple example. When we roll a die, right? When we roll a die, okay? Let's say we roll a 6-face die, okay? And it is a fair 6-face die. So the outcomes will be 1, 2, 3, 4, 5, and 6. These are what? The possible outcomes. So that's what we mean by these, yeah? 1, 2, 3, 4, 5, and 6. And what's the probability here? It's a fair 6-face die. So I have 1 over 6, 1 over 6, all the way up to here, which is 1 over 6. That's what we mean by 1 over n here. Okay, good. So this is the easiest discrete uniform distribution we can talk about. Okay, so I've given it a formal definition here. I've given it a formal definition. If you have random variable x with discrete uniform distribution, the probability function is given like this. Okay, probability x equals to small x equals to, sometimes we like to write it like this, right? And that's equal to 1 over n. And for x values going from 1, 2, 3, right up to n. Great. Enough about that, right? Okay, I wrote here, this is the standard case, right? This is the standard case simply because, you know, we can mess around with it a little bit, but we can do some transformations and still, I repeat, we can do some transformations and still bring it back to the standard case. Okay, never mind. Let's move on to some definitions. The mean, I'm not going into some proofs and all that. You can look up any normal, you can look up a statistics book or a probability book to get your derivations. So let's just state the facts. The expected value of x is what? N plus 1 over 2. Okay, this one here. The expected value of x is n plus 1 over 2, and the variance of x is n squared minus 1 over 12. Okay, this will come automatically to you, right? When you deal with a discrete distribution, and we're looking at the expected value of x is just n plus 1 over 2, and the variance of x is just n squared minus 1 over 12. Great. I want to talk about the probability generating function of this random variable. And that we know from our definition. Okay, we know from our definition. Remember, is the expected value of what? T to the power of x, remember? So there you go. Okay, I have values of k going from 1 to n. I have t plus t squared right up to t to the power of n, whole thing divided by, or rather whole thing multiplied by 1 over n. Again, the idea is not hard, right? Let me write it here. The idea is not hard. We are looking at the expected value of t to the power of x, right? So you start with, remember, x equals, you start with 1, right? So I have t, okay, times 1 over n, okay, plus, remember, it's a summation, right? And then I have t, second value is t squared, okay, times 1 over n, okay, I don't need this. Then go to the next one. Let me write one more. T cubed, okay, times 1 over n. Again, we are looking at x equals to 1, then x equals to 2, x equals to 3, right up to what? Good. X equals to n, right? So I have n times 1 over n. Okay, these are all the probabilities, yeah? So all the probabilities. So that's what I've written here. So it's easy for you to follow, except that, I put this in a bracket, no big deal. Then what happens? This one here, right? Okay, this one here, you can use the sum to n terms of a geometric series, yeah? I repeat, you can use the sum to n terms of a geometric series. I've written the formula here, a times 1 minus r to the power of n over 1 minus r, and then you can arrive at this formula, okay? Great. Then we have got the MGF, the moment generating function. I will talk about this soon enough, okay? The moment generating function is the expected value of e to the power of dx, yeah? Okay? So we have a summation again. It's an expectation. J going from 1 to n. The probabilities are good. It's just 1 over n times e to the power of jt. Again, we're using the sum to n terms of a geometric series, or if you like, you can call it geometric progression, and you'll get this formula. Okay? So that's what I wrote here. For both of these, we have used this sum to n terms formula of a geometric progression or a geometric series. Okay, enough about formulas. Let's look at some examples and wade our way through this. Okay, let me move it up. Yeah, give me a second. Okay, good. I'll clear the screen. And now we have example. Suppose X is uniform on 3, 4, 5, 6, 7, 8. Okay, again, right? X is uniform on 3, 4, 5, 6, 7, 8. We want to find the expected value of X and the variance of X. The first thing that should jump out at you, okay, is it's not starting at 1. Okay, it's not starting at 1, it's starting at 3. Yeah, so please be a bit careful. Our earlier examples, we wrote some formulas, X starting with the value of 1 and going right up to n. So here we are starting with 3 and ending with 8. So let's look at how we deal with the expected value of X and the variance of X. Now, so I wrote here, this is not the standard case. Okay, not the standard case since it begins at 3 and not 1. But we can do some mild transformation, right? How do you get 1 from 3? Just minus 2. Okay, so if you minus 2 here, you'll get 1. Minus 2 here, you get 2. Minus 2 here, you'll get 3, and so on, right? Minus 2 here, you'll get 6. So instead of dealing with these values, I'm going to call it as, instead of looking at it as this complicated problem here, if I can use the word complicated, okay, I am going to define x minus 2. Okay, and then I'll work with x minus 2, because the minute I take x minus 2, then I have a standard uniform, right? 3 minus 2 is 1, 4 minus 2 is 2, 5 minus 2 is 3, and so on, right up to 8 minus 2 is 6. So I'm going to work with the expected value of x minus 2. Excuse me, let me say it again. I'm going to work with x minus 2. Now, this is a standard uniform on 1, 2, 3, 4, 5, and 6. Okay. So the expected value of x minus 2, we can easily find. If you don't like that, right, what you can do is you can call this y, okay? You can call this random variable y. But I didn't do that. I just said, hey, let's just call it x minus 2. So the expected value of x minus 2, we know is expected value of x minus 2, okay? So um, this thing here, right? Now this, be careful, right? This is x minus 2. So what's the expected value of this? Let me write it here, right? In case you have an issue here. Okay, the expected value of y will be n plus 1 over 2. 6 plus 1 is 7 over 2. Okay, this is the expected value of y. Okay, and so the expected value of x minus 2 will be 7 over 2, right? So you can work out the expected value of x, okay, will be 7 over 2. Bring this negative 2 across, it becomes plus 2, and you'll get your answers. Let me say that again, right? Quickly go through this example, right? We are given a random variable x, okay? We are given a random variable x, and we are told it's uniform. And uniform on what? 3, 4, 5, 6, 7, and 8, okay? That's the random variable x. And we're trying to find what? The expected value of x, okay? So what you do, you realize that this is not a standard form. So why don't we change it to a standard form? So let's go ahead and call, okay, let's define a new random variable y equals to x minus 2. Now, when you do that, then you find that y will take values starting from, okay, 1, 2, right up to 6. So you work with y. This one here, you have standard formulas for it, n plus 1 over 2, right? That's the expected value of y. So I've done it here. The expected value of y is 7 over 2. But hey, y is x minus 2. We want the expected value of x. So the expected value of x, you need to just mess around with it, right? The expected value of x will be just be the expected value of y plus 2. That's it. Okay, expected value of y is easy because y is a standard uniform discrete random variable. So work on that, add 2, and you're done. You get the expected value of x. The same thing for uh, the variance of y. Okay, the variance. This is what we're trying to find, right? Okay, so this is what we want to find: variance of x. But work with y. Okay, y will be x minus 2. So the variance of y will be equals to the variance of x. Okay, we know that, right? The negative 2 doesn't change anything. The variance of y equals to the variance of x. In statistics, in probability, right, we say that the variance of a random variable is not affected by a shift or a scaling of this thought. Okay, so the variance of x minus 2 is the same as the variance of excuse me, the variance of this one here, right? The variance of y is the same as the variance of x minus 2. In other words, the variance of x minus 2 is the variance of x. Okay, great. So we can use n squared minus 1 over 12. So we have, what is n? 1, 2, 3, 4, 5, 6. Oh, yeah, good. So it's 6 squared minus 1 over 12, and you'll get 35 over 12. So the variance of x is just 35 over 12. I'm going to say that again in case any of you missed it. Okay, so let's start slowly, right? We have y equals to x minus 2. Okay, now take note, the variance of y will be equals to the variance of x. Okay, from here we can write, okay, the variance of y equals to the variance of x. Now, if you remember, right, I gave you a formula some time ago, the variance of ax plus b equals to the okay, equals to what? A squared variance of x. Same idea, right? Except that now a is 1, right? So 1 squared is 1. So uh, the variance of y here, okay, is the variance of x. Okay. Now, because remember, this is what you want to find, right? So let's go ahead and find the variance of y, because y takes values 1, 2, 3, 4, 5, 6. So the variance of y is what? 6 squared minus 1 over 12. So the variance of x is just this, and that's it. Okay. So what have I written here? For the general case, for expected value of x, take the average of the first and last values. Okay. For the general case, this is a note, yeah. For the general case, for expected value of x, take the average of the first and the last values. For variance of x, use number of values in range squared minus 1 over 12. Okay, let me say it again. For the general case, if you're trying to find the expected value of x, just take the average of the first and the last values. Remember, we are looking at, let's say, a general case. Let's say we talked about uh, uh, 3, 4, 5, 6, 7, 8, right? Let me just clear this, yeah? Okay. So I have, remember this is general case, right? 3, 4, 5, 6, 7, 8. Take the first and the last values, 3 plus 8, 11, divided by 2. The average of the first and last values. Okay, if you don't want to do any of this transformation thing, right? So if you want to find the variance, then number of values in range 1, 2, 3, 4, 5, 6. Okay, there's 6 values, 6 squared minus 1 over 12, and we are done. Okay. So that's taking care of the general case if you don't want to do any transformation. Okay, now let's look at another example here. I want to move the screen up a little bit. Okay. Okay. Good. I'm looking at my sheet of paper here so I can read it clearly. Select a number Z. Okay. At random. Again, select a number Z at random from 2, 4, 6 right up to 18, right? The even numbers. The even numbers 2, 4, 6 right up to 18. Select number Z. Find the probability that Z is bigger than or equals to 5. That's the first part. Okay. That's the first part. Okay. And then second part, find the expected value of Z. And then find the standard deviation of Z. Okay. The standard deviation of Z. Okay, great. So let's do it slowly. Yeah. So what is Z? Okay. Z is a number, it's an even number, right? To, let me write it here, 2, 4, 6, 8, okay, right up to what? 18, right? Good. So, what we can do is, we can write this as, okay, if we can write Z as equals to 2x, okay? Maybe x will go from, this is not hard, right? 1, 2, excuse me, 2, right up to 9. Does it make sense? So I'm just saying Z can take values 2, 4, 6, 8, 10, 12, whatever up to 18. So we are saying, let's define X, right? X can take values 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. X can take values 1, 2, 3, 4, 5, 6, 7, 8, 9. So Z must be what? 2x. Okay. There you go. Okay. Z is 2x. So this thing here is easy to handle. The expected value of X here is just what? 5, right? Take this value, add them up and divide by 2. The expected value of X is 5. Okay. 1 plus 9 divided by 2. So the expected value of Z will be what? 2 times the expected value of X. And you'll get 2 times 5 is 10. Easy. Okay. Now, the variance of X, this one you can easily get. Okay. The variance of X, it's what? 1 to 9. We have 9 values in the range. So it'll be 9 squared minus 1 over 12. Let me see where it is. Yeah. Okay. This variance of X is 9 squared minus 1 over 12. You can get the number. So the variance of Z, remember, variance of 2x, okay, will be equals to variance of Z, right? So this will be for variance of x equals variance of z. What is variance of x? Well, variance of x is easy to find, right? We just found it. What is this? 81 minus 1 is 80 over 12, which should be 20 over 3. We found that already. So multiply that by 4 and you'll get your answer. Okay, that's the variance of z. Okay, the probability that z is bigger than or equal to 5, well, you can write it like this: 2x bigger than or equals to 5. So x is bigger than or equals to 5 over 2. Okay, bigger than 5 over 2, bigger than 2.5, right? Bigger than 2.5, we have 1, 2, 3, 4, 5, 6, 7. 7 values out of 9. So the answer is 7 over 9.